In this module, we're talking about what are called quantum numbers. Quantum numbers are derived from or fall out of Schrodinger's equation and the wave functions that we're talking about. They help describe the wave function. You can think about quantum numbers as a set of coordinates, really, for where an electron can be in an atom. So we're going to go through, I'm going to talk about 3 quantum numbers. There's a 4th that we'll talk about in a later module called M sub s. So the first quantum number we're going to talk about is called the principal quantum number n. And the rule for n is that it can be any positive integer starting with 1, 1, 2, 3, 4, all the way out to infinity. And what it tells you about an electron in an atom is what shell or level that electron is in. Now, the larger n is, the farther out from the nucleus the orbitals in that shell can extend. And what that means is that the higher the value of n is, the larger the energy of an electron in that shell. Higher n, farther from the nucleus, higher energy. And the possible values. Now, this is a hierarchical scheme, which means that in order to know the possible values for the second quantum number I'm talking about, called the angular momentum or azimuthal quantum number, L, we already have to know what value the principal quantum number n has. So once we know what the principal quantum number is, then the rule for what possible values of L, the angular momentum quantum number there are, is this. L can be any integer starting with 0 up through 1 less than whatever n is. So if n is 3, L can be 0, 1, or 2. If L is 7, if n is 7, L can be 0, 1, 2, 3, 4, 5, or 6. If n is 1, then the only thing L can be is 0. Okay? And what L, or the angular momentum quantum number, gives you, it gives you the subshell or the sublevel. So we have the shell or the level from the principal quantum number, and within that shell there are subshells or sublevels. These are given by L. And knowing what value L has, we know what shape an orbital is in that the orbitals in that subshell are, and you'll see pictures of those in the next module. But for now, we also have abbreviations for different values of L. If L, for any subshell where L is equal to 0, we call that an S subshell. L equals 1 is a P subshell, 2 is a D subshell, 3 is an F subshell, and 4 is a G subshell. So remember this. So we usually call them S, P, D, and F. G, there's no element in the periodic table whose ground state at this moment requires a G subshell. The third quantum number, called the magnetic quantum number, or M sub L, just like we need to know what value n has so we can know what possible values M sub L can have, we need to know what value L can have. We need to know what value L has so that we know what possible values M sub L can have. The rule for what M sub L can be is that it can be any integer starting with negative L through 0 up to positive L. So for example, if L is equal to 3, that means that M sub L can be negative 3, negative 2, negative 1, 0, 1, 2, or positive 3. And M sub L, it ends up related to which direction or which orientation an orbital in that subshell is pointed, the orientation. But really the most important thing for us is that because each orbital within a subshell must have a different orientation, that the number of values that M sub L can have tells us how many orbitals there are in a subshell. If L is equal to 2, M sub L can be negative 2, negative 1, 0, 1, or 2. That's 5 values. And so we know that there are 5 orbitals in an L equals 2 subshell. Think about that. Make sure that's clear. So for example, if n is equal to 3, so remember we have to know what the principal quantum number is before we know what possible values L can have and then M sub L. Well, if n is equal to 3, L can be 0 up through 1 less than n. So L can be 0, 1, or 2. And And that means we have in the n equals 3 shell a 3s, a 3p, and a 3d subshell. Now within each of these subshells we have different numbers of orbitals. Every s subshell, that is when L is equal to 0, can only have m sub L equal to 0, and that means there's only one orbital in any s subshell. So there's a 1s, a 2s, a 3s, and all the way through 7s subshells, each having one orbital. It's a little bit, got to be clear what you're talking about, but in that 1s we call subshell, we say it's a 1s orbital. In the 5s subshell, we call that one orbital the 5s orbital. Okay. In any p subshell, that is when L is equal to 1, m sub L can be negative 1, 0, or 1, 3 values, so there are 3 orbitals. For example, in the 2p subshell, there's 3 2p orbitals. In the 3p subshell, there are 3 3p orbitals. Notice, by the way, there is no 1p subshell because p means L equals 1, and if n equals 1, L cannot be 1. That's impossible. It can only be 0. So 3 orbitals in every p subshell. Starting with 2, the n equals 2, there's a p subshell all the way up through, well, into infinity, really. D subshells, that means L is equal to 2. There are 5 values for m sub L. That means there are 5 orbitals in every D subshell. And the first time we see a D subshell is in the n equals 3 shell. Because if n is equal to 2 or 1, then L cannot be 2. Look back at the rules. So we have 5 orbitals in every 3D subshell and every 4D, 5D, 6D, 7D, etc. And a F subshell is n equals to 3. That means there are 7 values for m sub L, and that means there are 7 orbitals in every F subshell. The first time it's possible for there to be an F subshell is in that n equals 4 shell, 4F, 5F, etc. Each of these has 7 orbitals within it. So this is sort of a summary here. When n is equal to 1, L can only be 0. There's only one subshell. It's called a 1s subshell. And L equals 0 means only one value for m sub L, so there's only one orbital, a 1s orbital. N is equal to 2. L can be 0 or 1, 1 less than n, remember. And that means there's a 2s and a 2p sublevel, subshell, at n equals 2. The 2s can only have one value for m sub L, so there's only one 2s orbital. 2p subshell, there are 3 values for m sub L, 3 2p orbitals, and so on and so forth. Now, in every atom that exists, there are all of these orbitals, subshells, and shells, and more. But the only thing that's going to matter to us is which ones have electrons in them, and we'll get to that next module. So, for example, which of the following do you think is not a possible designation, which is not a correct designation for a subshell? 7F, 2D, 6S, and 6P. Right, 2D. Very good.